Hello friends, today I am going to talk about input-output organizations. So in this case mainly we have to see about the direct memory access. Before that let us have a look at accessing IO devices, interrupts and then go to the direct memory access. And then buses normally without a bus we cannot transfer the data, and from input output devices to processor the interface circuits are necessary, and then what are the standard IO interfaces we have to see. So first one, accessing IO devices, single bus architecture. So bus is nothing but it is a conducting line. It is used to exchange the information from one device to another device. Typically, bus consists of, there are three lines. It has to carry three types of signals. Number one, address, data, and then control signals. Each IO device is assigned a unique set of address. So, which IO device is called upon, the address of the particular IO device is to be sent via the bus. So in this case, we have to generate particular spaces for storing the address. So for that, we have to see about the IO mapping. First case, memory mapped IO. So memory mapped IO means if we specify an address, that same address will be used to address the memory location as well as IO device. There will not be any specific instruction for mentioning the memory location and IO devices. So here the memory is shared. Memory is shared, and no special commands for IO, and large selection of memory access commands available. So larger number of commands are available, but there is no specific commands for mentioning either memory or IO devices. With the memory mapped IO, any machine instruction that can access memory can also be used to transfer data to or from the IO device. So it is simply saying that address will be common for memory as well as IO device. And when building a computer system based on this processor, a designer has the option of computing IO device to use a special IO address. That is, depending on the architecture, IO device may have separate address space in the total memory space, total memory area. IO interface for an input device. So in this case, this diagram is shown. This is IO input device. Input device. It has to have interface, contact with the processor. So in between, we need to have IO interface. So directly IO device cannot have contact with the processor because of the speed that we will see it later. So in between we should use IO interface circuit. So the IO interface circuit is consisting of address decoder, control circuits, data and status registers. So address decoder means after getting the address data, it has to decode and recognize which IO device is called or addressed to, and then control circuit. It is carrying the control signals, and what control signals that we will see it in the next slide. data and status registers. So these registers will have some flags indicating the conditions that will also be seen later. So first one, address decoder, data and status registers and control circuitry required to coordinate I/O transfers constitute the device interface unit. So in between processor and I/O device there should be an I/O interface. So it will be connected to the processor. So processor means through buses only. And what are the buses? First one, address line, the bus which will carry data and the bus which will carry control signals. That is why address decoder is connected to the address line, and then control circuit, it is connected with the control line. Data and status register is connected to the data line. Next one, I/O techniques. So how to call upon the I/O devices? So there are three techniques. Number one, program controlled I/O, interrupt driven, and third one, direct memory access. So this direct memory access is the main topic in this lecture. And first one, let us see program control I/O. So consider a simple example of I/O operations. So input means through keyboard we are giving the input to the processor, and display means it is the output device through which we can read the data. I mean we can read the output from the computer after calculation. There are four registers, and what are they? It will be seen in the next slide. And two flags KIR, so keyboard interrupt request, and DIR, data interrupt request. These two are the two flags which is available in status register, and they are used in conjunction with the interrupts only. So if they show the status or condition, then it is automatically meaning that it is the interrupt. So I/O devices are interrupting the processor. So here those four registers. So in the previous slide we have seen there are four registers. Number one, data in register, and number two, data out, status register, and control register. Data in means it is nothing but 8-bit of data is available in the data in register. It will be applied to the processor. And data out, it is also 8-bit register. It will be having the output from the processor, which output means it is the results of the calculation. And then status register, it is having the 8 fields are there, and the last four is DIRQ, KIRQ, S out and S in. And control register, it is having the main required flags are DEN and KEN. So DEN means display enable. It is output unit is enabled. And KEN means keyboard enabled. It means input devices enabled. So registers in keyboard and display interfaces. Number one, DIRQ, display interrupt request bits. It is asking for the display request, and KIRQ, keyboard interrupt request bits. It is asking for the input to the processor. So it is already seen display enable bit and keyboard enable bit. Next one, the processor repeatedly checks the status flags to achieve the required synchronization between the processor and an input or output device. So processor should know what operation it has to do. It has to do whether input or output, and which device is putting the request for service. So that is why the processor is continuously checking the flag bits of the register. We say that the processor polls the devices. So checking means it is nothing but it is polling the each and every IO devices. So polling means it is asking for interrogating each and every device, each and every IO device, whether it is required, whether it requires the service from the processor. So there are two other commonly used mechanism for implementing IO operation. The first one, interrupt and direct memory access. So interrupt means synchronization is achieved by having IO device and a special signal. So interrupt signal is sent to the processor, indicating that IO device is waiting for the service, So over the interrupt signal, special signal is passed over the bus whenever it is ready for the data transfer operation. So whenever the CPU is ready, then IO device is sending an interrupt signal over the bus. And then DMA. So DMA means the transfer of a block of data, not 1 bit or 2 bits or byte. A block of data is transferred from the input device to processor, and it is directly done. That is direct memory access, and it will do with the minimum intervention of the central processing unit. So direct access from the memory to IO devices, and not single bits or byte, a group of a block of data at the time it is transferred from and to the memory or IO devices. To avoid the processor being not performing any useful computation. That means if the processor is idle, then high priority hardware signal called interrupt. So in the previous slide we have seen interrupt means interrupt signal is sent by the IO device to the processor, saying that it needs the service from the processor. So at least one of the bus control lines called an interrupt request line is usually dedicated for this purpose. So control line means it is used to transmit the control signal. Here it is interrupt request line is nothing but the control signal only. It is requiring the service. That is why for sending the interrupt signal, there is a dedicated line called as interrupt request line and interrupt service routine. So for performing interrupt, there is a small program ISR, that is interrupt service routine, usually is needed and is executed when an interrupt request is issued. That means the processor is continuously doing its own execution, its own processes. But in between one IO device requires the processor service, then immediately it will send the interrupt signal. So after getting the interrupt signal, the control transfers to ISR, which is stored in some other memory location apart from these consequent memory addresses. So in that ISR, during that period, the IO device complete its transaction from the memory to processor, or IO to processor, or IO to memory, whatever it may be. Anyway, data transfer occurs during this period. An interrupt acknowledge signal serves this function. So if input device sends an interrupt signal, the processor has to accept, okay, I am ready to serve you. That will be indicated by sending the interrupt acknowledge signal. After that, it it will go to the ISR and then data transfer is getting completed. So next one, so how it is transferred? I have already shown through the mouse. In between, this is the main program. In between, if any IO device requires, the control will transfer to ISR. So in this case, ISR is nothing but in the previous slide I have explained about the transfer of data. But here print output device is requiring some print function. That is why after completing this print function, it is getting back to the original main program. This is what displayed in this diagram. So next one, interrupt. So I told interrupt means I want this service so that I am disturbing the processor for the request. I am disturbing the processor for doing my work. That is the interrupt. In that case, there are two types. Number one, hardware, and number two, software. Hardware interrupt and software interrupt. In the hardware interrupt also there are two subdivisions, namely external and internal. So external means the interrupt comes from the external forces, namely power failure or data path error, control error, so status transfer, hardware error. So these are all the external forces, and it is due to this if interrupt happens, then it is called as external hardware interrupt. And now internal. What is internal? It is due to the program only. If the code becomes wrong, erroneous code, erroneous data, instruction, wrong instruction, illegal opcode, and correct time it is unable to get the data means it may be due to register overflow, stack overflow, violation, formal violation, and then protection violation. Due to these reasons, these are all coming internally due to the codes. That is why these are all named as internal hardware interrupt. And one more subdivision, namely hardware interrupt is divided into maskable and non-maskable. So non-maskable means it cannot be retained. So if you press the reset switch, entire thing will go off. So we can if you make the processor to wait for some time, it is utter waste. How long it will wait? It will be waste only because entire thing goes off. But maskable means during an execution, a small high priority interrupt occurs, then it has to delay, it has to wait, and after completing the high priority service, it will come back to the original. So interrupt means we should not think that entirely the processes, the processes are abruptly stopped. It is not the meaning that just we have to wait for some time. After completing the higher priority work, the processor will come back and retain the work, resume the previous work. So only thing it has to wait and some time delay will happen. That's all. And next one, software. So software means, suppose in the program, if condition occurs, if else condition occurs. So if else means we know that the condition, if the condition is satisfied, go to that particular location. If the condition is not satisfied, go to the next instruction. Like that, we will give the condition in the program. So based on that, the control will transfer to some other memory location. Not the execution will not happen in the consequent order. So in this case, first one, normal. So software, there are two types. Number one, normal. So normal means by software instruction. By software we are giving. If code we are giving, that is why the sequences are disturbed. And then exception. So exception means normally any number divided by 0 should not come. Suppose if it is coming, it is violating actually. That violation is called here as exception. It will not happen frequently, but sometimes if it is happening, then it is known as exception. So next one, interrupt service routine. We have to talk about the ISR because control transfers to the ISR routine. ISR routine, I told you, no. So whenever it faces the interrupt, it has to branch to the ISR during which at that time the transfer of data or print or input work, whatever it may be, it will be executed. So first one, a subroutine performs this ISR performs a function required by the program from which it is called. So which device is calling, that operation will be performed through ISR. And next one, ISR may not have anything in common with the program. It is unrelated to the main program. That is why ISR is stored in some other memory location. It is not in combination with the or sequential with the original program address. And then, in fact, two programs often belong to different users. So, ISR may belong to some other user. Main program may belong to current user. Okay, that is why two different users. It is not necessarily belonging to the same user. It may belong to the different users also. By executing ISR, any information, see, this is important. Before transferring to the ISR, that means before starting off the ISR, we have to think, suppose the main information is going to be changed, it is going to be altered, means that information should be saved temporarily, and at the end of the ISR, while returning to the main program, whatever the information saved temporarily should be brought back, and then it will continue the main program. So it is important to, while executing ISR, when it is starting the ISR, if we think that from where it transfers in the main program, some important information is going to be changed just because of this ISR execution, then we have to store this information temporarily and execute this ISR, and at the end of the ISR, it has to take the information where it is stored and then resume the original information. And then address, no need to say, address of the next instruction will be saved in the program counter. So that after taking the address of the next instruction from the stack, because in the first module we have seen about the stack, while it is a special purpose memory location, it is used to store the address of the next instruction whenever the branching occurs. So it will take the address from the stack, and then it will continue from the next instruction. Next one, interrupt latency. So latency, due to interrupt, some delay will happen. That is what interrupt latency. So processor says only the contents of the program counter. Processor says only the content of the program, because due to interrupt, it has to resume the program. Means the program counter content is necessary for continuing the execution in the main program, and any additional information that needs to be saved, that already I told in the previous slide, it has to be saved, and when it is coming back, it has to terminate the saved program, and delay is called interrupt latency. So going back, going to the ISR, and before that saving the main information, and when it is completing ISR, it has to take the saved information. So for these all, some delay, time delay may happen, and this is known as delay interrupt latency. This time delay is called as interrupt latency. And then identify the interrupting devices. So the processor, how it will find out the IO device which is calling for the service. The simplest way to identify the interrupting device is to have the ISR pole. So whether you have interrupted, how many IO devices are connected to the bus of the processor, every devices will be asked by the processor that whether you have interrupted, whether you are asking for my service, it has to poll. That is ISR poll, all the devices. And its main disadvantage is the time spent in interrogating all the devices one by one. All the suppose n number of IO device means if we assume 100 device, 100 device it has to ask for. So that is why interrogating all the devices will automatically take the time. So time will be spent more. Next one, vectored interrupt. As we have already seen, if or else condition are interrupting, then the control will transfer to the ISR. So ISR will be saved in the some other memory location. I told you. For that particular memory location, if the control transfers, then it is known as vectoring. It is known as vectoring, that is branching to the particular memory location, I mean ISR memory address. The device requesting an interrupt may identify itself directly to the processor. So IO, while giving the interrupt, automatically it gives its identification number. So for the, if it recognizes the number, then automatically processor knows which device is calling for. Then the processor can start executing the corresponding ISR. Suppose if the print option, then printer has ISR which is stored in the specific memory location. Suppose if input operation, so input devices for the keyboard, ISR is stored, specific ISR is saved in the some memory location, memory. So based on the ISR memory address, the processor will transfer, I mean vector to the particular ISR. So in this way, it identifies which IO device is calling for my service. So this is called vectored interrupt. So each interrupt has memory address to access, separate memory access. So there is no confusion in identifying the device. The method of pointing to this memory location is vectored interrupt. So once a print option means, immediately it will transfer to print ISR. So this is called the vectored interrupt mechanism, and the process of running appropriate code is ISR. So it is print ISR and interrupt priority. So there are 5 priority, as I have already told you that it is default. Normally 5 interrupts will be available in microcontrollers, and these interrupts are divided based on the priority. So 5 categories. So if it is doing low priority interrupt, and in between before completing that low priority interrupt, if higher priority interrupt occurs, immediately it will stop the low priority interrupt and go to the and solve and complete the high priority interrupt and come back to the low priority. The next one, direct memory access. So there are 2 types of mechanisms. Number 1 interrupt and number 2 DMA. So these 2 are the types of IO mechanism. Interrupt we have already completed. Now coming to the direct memory access. So in this first one, direct memory access means not 1 bit or 2 bits. The group of data, a block of data will be transferred between the I/O devices and the memory. To transfer large block of data at high speed, a special control unit will be provided between an external device and the main memory without continuous intervention by the processor. So now our aim is to transfer a block of data from or to the I/O device to the main memory. But high speed okay, but large volume of data means all time if processor is intervened, I mean the processor is doing that task, then automatically the system performance will become degraded. So at just a transfer of data only. It is not performing any function, arithmetic logic function, any operation, only transferring data. So if we involve the processor all time, then automatically it is waste of time. The system performance will become degraded. That is why there is an interface circuit, DMA, a direct memory access controller. It is an interface circuit which is provided in between processor and I/O devices. Okay. So this approach is called direct memory access. Direct memory access. DMA transfers are performed by the control unit only. So DMA controller has the control unit which is the main cause for transferring the data. DMA, the control circuit, that is part of the I/O device interface. So it is interface only. DMA circuit is nothing but the interface only, and it is having the main part DMA controller, and through which it is able to transfer the block of data. We refer to the circuit as a DMA controller. Since it has to transfer block of data, the DMA controller must increment the memory address for the successive word and keep track of number of transfers. So it is the main function performed by DMA controller. How many number of block of data is transferred, that is important. And next one, what operation is performed, in which direction the data is transferred to and from memory, to and from I/O device. So the direction of movement of data and block of data, how many block of data, and sequential order. The address should be in sequential order, one by one, not in random manner. These three are controlled by the DMA controller. Although DMA controller can transfer data without intervention of processor, it is actually intervention of processor is minimal. So we cannot say without the intervention of processor. The processor has to initiate through the DMA controller and coming back to its main execution. And after completion, it will release the DMA controller and take over that. So it starting is done by the processor only. So with minimal intervention of processor, not a whole control by the processor. It will hand over the control to the DMA controller for transferring the block of data. So in this case, a small directional diagram is shown here. The CPU I/O device wants data to and from CPU. So input device means it has to give the input to CPU. Output device means it has to take the data from the CPU. That is why bidirectional arrows are shown here. In the same way, for performing the operations, it will take the data from memory and to memory. That is why bidirectional from memory to CPU. But now, just because of DMA controller, we can transfer the data to and from memory to IO. So both bidirectional, IO to memory and memory to IO. Bypassing the CPU, that is the main point here. So CPU starts and going out from that scene. So bypassing CPU, the data will be transferred from memory to IO or IO to memory, both way possible. So this is the main small diagram showing the relationship by the relationship of the operation done by the DMA. It enables a data transfer between memory and IO with minimal intervention of CPU. But processor control, so every control is held by the processor only. So load on CPU reduces. Control only, but it will not involve. That is why the load on CPU is reduced. The whole operation is done by CPU means CPU time waste, CPU is overloaded. By having DMA, the CPU gets underloaded and efficiency increases because CPU will involve in doing other high priority operations. That is why the efficiency of the system will become increased. And then CPU initiates DMA by sending starting address. That already I told you. DMA DMA operation is initiated by CPU, but it has to send the address of the data, starting address of the data. So automatically, because DMA will increment the address. Already we have seen in the previous slide. So DMA one by one it will increment the address so that in that block the all consequential in all consequential addresses what are the available data will be transferred. So number of words, how many words in the block, and the direction of transfer from IO to memory or memory to IO. This direction, these three are controlled by the CPU only, processor only. When transfer is completed, DMA informs CPU by raising interrupt. So my task is over and it will take the control. And next one, DMA contains address register. So I told you address register, the memory address register means the starting address of the data. And then control register, so direction of transfer to and from. And then word count, how many blocks are transferred. That count will be maintained by DMA controller. Okay, then working of DMA. It shares bus with CPU. So whenever it needs the data transfer, it takes the bus from the CPU, takes not dedicated, it will share the bus from the CPU. And then transfers IO to memory, memory to IO. CPU stops execution of the current program. Why stops executing the current program? It has to initiate the DMA for transferring the data from or to IO and memory, and increments PC, increments the address of the next instruction. This has to be stored in the stack. When the CPU comes back, it will take the address of the next instruction from the stack and then resumes the original instruction, original program. Moves the data, that means PC content to stack. PC content means address of the next instruction will be stored in the stack. And next one, it sends a DMA select signal to DMA control over the address bus. So address bus, what for it is used to send the address of the data block in starting address. If DMA is free, then it requires control of bus from CPU, because in the previous slide I told you the bus is shared from the CPU by DMA for transferring the data. It is sharing the bus by raising bus request. I need bus. So bus request signal is given by the DMA. CPU grants the bus. If it is having bus, free bus, then it will grant the bus. It will give the bus to the DMA operation. The CPU initiates the DMA by sending starting address and a number of words, a direction of transfer. All three will be sent by the CPU too. Now DMA transfer start. Next, CPU does not wait and resumes program. So once if data transfer is started, it will not wait until the data transfer is completed. It will come back to the main program. How it will come back? The address of the next instruction is stored in stack already before going to ISR. So it will take that address of the next instruction and come back to the main program. After completion of data transfer, now bus request is disabled because no more bus is required for this DMA, so it will take over. BG bus grant is disabled because bus request is granted by the processor. No, that is also disabled. Bus control goes to CPU. Now all bus will go to the CPU control. And that whatever I have explained till now, it is explained in this diagram. The address bus buffers, data bus buffer. So all are connected to the address register, word count register, control register. So control means in which direction data is to be moved. Word count means the count, number of memory block. And then address means starting address of the memory block. And then in this control logic, DS, RS and RD, read, write, bus request, bus grant and then interrupt. So the first one, IO device has to send the DMA request, and DMA, if suppose if it is free, it will send the DMA acknowledge and then the remaining thing will start. Next one, so how the data transfer occurs by the DMA controller, the same, it is the main memory, RAM, IO peripheral device, DMA control, CPU. So bus request in both way direction it is sent by DMA. Bus grant, it is also both way direction, DMA control to CMA. And interrupt, once if IO device gives interrupt signal, then automatically interrupt from the DMA controller to interrupt CPU, and then read, write, address data. So read means read to RAM, read only random access memory, data read and data write, and then address of the data, starting address, and the data will be moved to IO peripheral device. Here address select block is available. Next one, mode of data transfer. So data transfer, block of data is transferred, I told you. But in this case also, there are different mode of data transfer. What are they? Number one, burst mode. Second one, cycle stealing mode. Third one, transparent mode. In case of burst mode, DMA handovers buses to CPU only after completion. So this means that even if the CPU requires bus for performing some higher priority operation, this will not give the bus to the CPU. That is bus to mode. CPU has to wait, no other way. It has to wait. Even higher priority interrupt also it has to wait because buses will not be returned to CPU by the DMA controller in this bus to mode. And in the second, cycle stealing mode. So cycle stealing means after one byte of transfer, DMA gives back the CPU bus to the CPU. So at that time, if CPU wants to perform high priority interrupt, then it will perform, and then again it will give. It will be with the CPU, and once again the DMA takes the bus and transfers one byte of data, again giving it to the CPU. So in this way, for every transfer of one byte of instruction, since it is giving the bus to the CPU, during that time the CPU is able to perform the high priority operation, so that CPU no need to wait. But in bus mode, it has to wait. But here CPU does not wait. And in transparent mode, third case, DMA only CPU is executing instructions in which it does not require bus. So CPU is always busy with performing operations. In between, at one or two cases, suppose if it does not want buses, then only that buses will be taken by the DMA for transferring the data. That is transparent mode. So it will take whenever it is not used by the CPU, otherwise it will not be given to DMA transfer. And next one, buses. So in this case, till now we have seen through the buses only the data is transferred. So we need to know about the buses. So bus is the main feature here through which the data is transferred. So bus is nothing but it's a conducting line. So how the transfer is happen, and what are the buses types we have to, in which mode, in which way the data is transferred through the buses. These are all we are going to see in this category. So number one is synchronous data transfer. So synchronous means by the name itself we know that which device is sending the data, which device is receiving the data, both should operate in synchronization with one another. Now, in synchronization with one another means which is the root cause. Only thing, clock of high rate, high frequency will be used to coordinate the functions of both the devices. So definitely without clock signal, synchronization will not happen. So first one, in synchronization data transfer, sending and receiving units are enabled with the same clock. So different clock, no, because even suppose if you are giving the same clock rate, suppose 20 megahertz, both it is applied with 20 megahertz, even though a certain amount of problem will occur, delay will occur because of the characteristics. That is why from the main clock tree, it has to supply both the devices because the features should be same, characteristics should be same. Both the clock signals should be identical. That is why from the same clock tree, both the receiver and sender should take the clock signal, not separate signal, even if the clock rate is same. And it is possible between the two units when each of them knows the behavior of the other. Each one, the sender knows the behavior of receiver, receiver knows the behavior of sender, because both are supplied in the same clock frequency. That is why each knows one another. The master performs a sequence of instructions for data transfer in a predefined order. So automatically that order in which the data is to be transferred, it is known by the master, because master is to do the function, is to do the operation. All these actions are synchronized with a common clock. The master is designed to supply the data at a time when the slave is definitely ready for it. So it knows slave is ready. Whenever slave is ready, it will start the transfer of data. And next one, usually master will introduce sufficient delay to take into account its role. See, here master is normally master is server only. It has to supply the data to all slaves. Slaves are nothing but all the slow speed IO devices connected to the master. So in this case, we know that master is at high speed, slaves are at slow speed. So knowing that slaves are at slow speed, whatever the speed at which the master is delivering the data, the slaves are unable to receive the data at such a high speed. That is why, since it is known to the master gives every time that delay. So it is slowly giving the data to the slaves so that it allows the slaves to receive the data correctly. It is letting the slaves to receive the data correctly. So you should, and then what is the next point? Flow response obviously without any request from the slave. Slave will not request, I am slow, you give the data in correct time. No, there is no response from slave. There is no signal from master also. No signal, because already I told you that both are knowing each other. That is why I am going to send, it will not convey. I received, all you have sent, it will not convey. So there is no signals indicating the operation. The master does not expect any acknowledgement signal. So I have received all the signal. This will not be intimated by the receiver from the slave. Then the data is sent by the master to the slave. And then similarly, the data from the slave is read by the master. Suppose if the data is sent by the slave, the master will not indicate that I have read your data. Neither the slave informs that the data has been placed on the database, nor the master acknowledges that the data has been read. So slave will not indicate that I have kept the data in the database. And after receiving, the master is also not indicating that I have taken your data from the database. I have read your database. It will not. Both way indication is not possible. Both the master and slave perform their own task of transferring data at a designed clock period. So already it is an ultimate clock period only. Prior to transferring data, the master must logically select the slave either by sending the slave's address or sending a device selected signal to the slave. Suppose if any slave wants to have the data transfer, the slave has to send the address. Otherwise, in the second category, suppose master wants to send the data to particular slave, the master is to send the address of the slave. So in this way, data between any particular slave and processor is happening. But there is no acknowledgement signal. This is permanent. Already I told there is no signal between the processor, master and slave. So in the timing diagram is shown here how the synchronous operation is. For example, read operation. So it is one clock period. So one clock period means it is a square wave only, but half is off period, half is on period. One half of the on period, half of the off period is equal to one clock period. So here it is falling edge and it is also falling edge. So in this both falling edge, address of the slave is sent by the master. Is sent by the master because that slave's data is to be read by the master. And then read signal by master. I want to read your data. So first in the both falling edge, address of the data is put, and then read signal. What I want to do, I want to perform the read operation. That is why read operation is sent, read signal is sent by the master, and then this during this on period of the clock, it is off period and it is on period. Both the period is utilized for sending the address of slave and operation signal. I mean a read signal or write signal. Both will be utilized. But during the on period only, the data is placed in the data bus by slave. The addressed slave is putting its data on the data bus. Next one, in this timing diagram, so already we have seen that the timing diagram, master first places slave address. So by the diagram we have already seen first slave address and then read signal. It wants to read or write, that the read signal is sent. The entire read operation is over during that. So during the on period, the slave, the particular slave is putting its own data on the data bus. So entire three operations are done completed during one clock cycle. And the features of synchronous data transfer. So what are the features? The first one, timing. The data transfer is synchronized with the same clock. That is first feature. That is generated by the sending device and used by both, because sender is important here. It is almost equal to the master. So it is having the whole control. Means it is having the main clock. So from which it is supplying the clock to receiver. Sending the generated by sending device and used by both sending and receiving devices. This ensures that both the devices are in sync. So same clock will sync and ready to receive or transmit data at the same time. Same time. So no, there is no time delay. And data transfer modes, here what are they? Synchronous data transfer, either in serial or in parallel. So parallel means 8 bit at a time. Serial means 1 by 1. So one line will be provided from LSB to MSB, 1 by 1, 8 bits are transmitted over a single bus. But in parallel transfer, 8 number of buses will be there. And then data rate. So data rate, what is data rate? It is defined as the number of bits transmitted per one clock cycle. Number of bits transferred per one clock cycle. It is the data rate. So that this data rate is the number of bits means it is depending on the clock frequency only. If high frequency, the total number of bits transmitted per one clock cycle, one clock duration will be more. So we have to ensure that the clock frequency is as much as high. And however, synchronous data transfer can be faster than asynchronous data transfer because there is no need to add, there is no need to add extra bits for synchronization. So here in synchronization, in synchronized data transfer, only we are sending the data. In asynchronous, there will be head bit and tail bits that we will see it later. But in synchronous data transfer, only data is transferred along with the clock. Clock is enough. There is no need to have a sync pulse for coordination or indication of the starting clock or indication of the ending clock. Nothing, no more bits are, no more extra bits are necessary. And then transmission line. So transmission line means already clock, character, everything okay. But for any transmission, we need to consider the impedance. Both the devices should be terminated in the same impedance. Suppose the impedance is mismatched, this will cause the reflection. Due to the reflection, the data will be lost. A signal will get wasted. That is why impedance matching is important. Both devices should be terminated in the same impedance. Advantage of synchronous transfer. So it is easy. Both are coordination with one another. Master does not wait. That is important because master carries the all control. If it is waiting, the time will be wasted and it will affect all slave operation. That is why. And does not wait. And there is no need to indicate the starting of the data transfer, ending of the data transfer, and requesting the transfer and acknowledging the nothing more. And disadvantage, slow speed is connected to the common. Bus is shared by the master as well as slave. So master is high speed, slave is slow speed in the same bus. So anyway, master has to wait for some time to let all slaves receive the data. So at that time, it has to wait. Means it is waste of time. It can degrade the system performance. If the slave operates at slow speed, the master will be idle. Otherwise, it has to wait. Wait means idle only. So during that time, the processor will not do any function. So processor time is wasted. In the same way, master is speed. Otherwise, vice versa. Otherwise, suppose if slave is transferring the data to master, the slave is slowly sending. So for this also, that time also master has to wait in receiving the data. Both way transfer anyway master has to wait, so it will affect the system performance. So in this case, up to this we have seen the synchronous data over the bus, synchronous data transfer over the bus. In the next video, we will see the asynchronous data transfer and how far it will be compared with the synchronous, how it is useful, what is the features, what is the advantage, what is the disadvantage, everything we will see in the asynchronous transfer. Because all time we cannot say synchronous is useful, asynchronous is not useful, because asynchronous data transfer is adaptable. When the speed is mismatched, it will be adaptable for the data transfer for any operation. So thank you all.